Conversation on our last topic. Uh, so let me share my screen. We were talking about implicit differentiation and other techniques of differentiation. Uh, right. So the implicit differentiation is a technique that we use to differentiate implicit functions. Functions that are not explicitly written in terms of x. The typical examples are circles. Y square plus x square equals r square. All right. Can you see my screen? Right. Okay. I'm not using my personal computer today, so it is quite difficult to navigate through this. Okay, so we were talking about implicit differentiation. This is the technique that we need to differentiate implicit functions, functions that are not explicitly written in X. So for these functions, you can see uh, powers of X, powers of Y, or some functions of Y, functions of X, combined in various different ways. Um, as I said before, the typical example is a circle. Hmm? So to differentiate a circle, the unit circle x square plus y square equals 1. we typically take the equation. Usually we need it as a function of x. So we need y equal some expression of x. But here, instead of making y into the subject, we take the equation and differentiate it. So derivative of x square is 2x, derivative of y square is 2 times y dy over dx. So we can see that the derivative appears as the derivative of y. So still we think of y as a function of x and differentiate both sides. So we talked about how we can use this to differentiate various uh, implicit equations and also inverse functions. If you have something like y equals sine inverse x, the analogous implicit equation is sine y equal x, sine y equals x. So in that way, now we can differentiate both sides using the implicit differentiation. At the end, once we uh, write everything again in terms of x, the derivative in terms of x, we get the derivative of sine inverse function. Okay, so we cannot have any y terms in the derivative because what we were trying to do is we are trying to differentiate sine inverse of sine function. Right? uh, Let me try to show you the derivative of uh, some other familiar functions. A to the power x. We know the derivative of e to the power x. It is just e to the power x. Here, a means an arbitrary uh, positive real number. Arbitrary positive real number. It could be 2, 3, 10, whatever the number you want. To differentiate this function, since we know the derivative of e to the power x, we can use that. So what we can do is we can take a to the power x and write it as some power of e, some power of e. A to the power x is e to the power of x times ln a. So how can we come up with this expression? How can you see a to the power x equals e to the power x times ln a? For that, you can use some log rules. So think about the exponent x ln a. That is same as ln of x a to the power x. Ln a to the power x. Anything in front you can bring to inside, and by making it to uh, making it the exponent. So x ln a is same as ln a to the power x. Now this x is gone. You have e to the power of ln a to the x. And e and ln are inverses of each other. So they cancel each other, leaving you just a to the power of x. So this is the trick that we use to change the base of an exponent. Instead of e, you can have any real number. A to the power x equals b to the power x log b base a. Log b base a. Now that now we have a to the power x as e to the power something, and we know the derivative of e to the power x. It's just e to the power x. So take, instead of differentiating a to the x, now we can differentiate e to the x ln a. Take that and differentiate. And again, here we have a composition of two functions. It is not just e to the power x, e to the power some expression of x. So it is a composition of two functions. The outer function is the exponential function. Inner function is x times ln a. Now let's differentiate this outer function. Let's you differentiate e, keep whatever inside it. So it's x ln a. Then derivative of inner function, derivative of x ln a. It is some constant times x. So the derivative of a constant times x is the constant ln a. Now, if you want to change everything back to a to the powers of a, this front term e to the x ln a is a to the power x. So a to the x ln a. In the same way, we can differentiate log b base x. Uh, Logarithm of x in base b. For ln, for b equals e, from the natural base, we have an expression. It is 1 over x. But once we have an arbitrary base, again we can use the same trick that we use to differentiate a to the power x. We can rewrite log b base x in terms of log e base, log base e. There is a base change formula for logarithms. You should have seen this in your O-level class, I think. Changing bases. So using this base change formula, we can write ln b base x, log b base x as ln x divided by ln b. Now take the right hand side and differentiate it. Keep in mind that log ln b is a constant. It has no x terms in it. So 1 over ln b is a constant. You don't need to use the quotient rule. So this is some constant times ln x. You just need the derivative of ln x. So sometimes it is good to know these derivatives. Because now you can differentiate a whole bunch of other functions, like e to the power x, like pi to the power x. This is like a to the power x. Now a equals pi. So this is, we already know this should be a to the x ln a. So pi to the power x ln pi. Right? Then logarithmic differentiation. This is one of the simplest technique that we can use to transform very complicated functions into simple functions and then differentiate. Logarithmic differentiation is a procedure in which logarithms are used to trade the task of differentiating products and quotients for that of differentiating sums and differences. So the idea is, say you have a very complicated function containing products, quotients, and powers. Once you take the derivatives logarithm, products turns into summations, quotients turn into differences, and powers turn into these constant multiples. ln 2 to the power x is x times ln 2. So that is the idea. So think about this function. Find dy over dx for y equals this complicated function x to the power 3/4 times square root of x square plus 1 divided by 3x plus 2 to the power 5. Usually we need to use the quotient rule because this is a product of two functions. Quotient of two functions. And when we apply the quotient rule for to compute the derivative of numerator, we need to use the product rule. Not only the product rule, we need to use the chain rule multiple times. So this function, even though the expression is not that long, it is a very complicated function. It contains lot of parts, lot of moving parts are in the same expression. And if you look at this carefully, you can see it is not a sum of two functions or difference of two functions. It is a quotient and products and powers. When we have this kind of a function, we can easily turn it into a summation, sums and differences using the logarithm. Now take both sides and take the logarithm. Left hand side is simple, it is natural log of y. For the right hand side, some kind of funny thing happen. So in the numerator we have a product. So it turns into a summation and denominator becomes a negative term. So ln x to the power 3/2 plus ln square root of x square plus 1 minus ln 3x plus 2 to the power 5. That's it. And we can bring all the exponents to front. So 3 divided by 4 becomes a coefficient here. And this power 1/2 becomes another coefficient. This power 5 becomes another coefficient. Now, in the bottom, we have a very simple expression. It is no longer complicated as it was at the very beginning. Now you can take this very last equation and differentiate both sides. And to differentiate the left hand side, you will need the implicit differentiation. To differentiate the right hand side, you only need the derivative of ln x, and for the second two terms, you will need the chain rule. That's it. No quotient rule, no product rule, and you won't see anything complicated. So take both sides of the equation and differentiate it term by term. The left hand side, again it is a composition. The outer function is ln, inner function is y. Derivative of the outer function is take the reciprocal of whatever inside it. So natural log of, that's the derivative of natural log. So 1 over y dy over dx equals 3 divided by 4 is a constant. So we keep it in front but don't do anything to it. So keep it, differentiate ln x. It's 1 over x. Again, keep 1/2 and differentiate the inside. Again, you can see it is a composition. So 1 over x square plus 1 times derivative of the inner part, 2x, minus 5. Minus 5 is this constant in front of this third term. Then derivative of ln is 1 over 3x plus 2. Derivative of the inner function, 3x plus 2 is 3. We can simplify this right hand side a little bit But you don't need to add these fractions by uh, by writing the common denominator. You don't need to take the summation. It will make things complicated. It looks simple now, but when you try to compute it, it will become messy, and most of the time you will make some algebraic mistakes. So better to leave it in this way. And to isolate the dy over dx, you can multiply both sides by y. And we know y. Y was the initially given function, so you can write uh, that expression instead of y. So derivative is now y times these sum of fractions that we come up with. All right, so that is the derivative of this complicated function. We avoided using quotient rule and product rule just by taking the logarithm of both sides. So we took the logarithm before differentiating it. This is called logarithmic differentiation. It is not a complicated rule. It simply says if you have a function uh, composing of products, quotients, and powers, better to take the logarithm before differentiating it. But by taking the logarithm, we can simplify it. We can make it less complicated, right? Think about this function: x to the power square root of x. Um, can somebody tell me the domain of this function? Can somebody tell me the domain of this function? If it's okay if you don't know the exact answer, but you can still guess. We already know things about domains of functions. There are two things that we are not allowed to do. We are not allowed to divide by zeros, and also we are not allowed to take square roots of negative numbers. Thank you, Ashmita. Uh-huh. Thank you, Tarini. Okay, I got two answers. Uh, the first answer says x bigger than or equals 0. The second answer says from 0 to infinity, not including 0. So we all can agree that this function is well defined for positive real numbers. We have a problem at 0 because it becomes 0 to the power 0. 0 to the power 0 is another undefined term, or as we call an indeterminate form. Um, so it is better to exclude 0 from the domain. The function will be well defined for all positive numbers, but not for negative numbers. 0 has this very uh, like it is in the middle. It is in the middle. In one side it is okay, on the other side it is not okay. So now one can ask for the limit. What if you take the limit as x goes to 0 from the right hand side? Whenever you see something like this, we know the function is undefined at 0. Function has a problem at 0. So you can ask whether still we can take the limit. you can ask for the right limit as x goes to 0. Uh, you will see actually we can compute the right limit, and there is a very nice technique for doing it. It is called the L'Hopital's rule. We will learn it as an application of derivatives in one of the upcoming sections. So this function is very well defined for positive x values, and it has a limit at 0, right limit at 0. So if you want, you can actually include 0 in the domain by assigning the limiting value for the function. You cannot simply substitute x equals 0. Uh, you need to find the limit and redefine the function by assigning the limiting value as the function value at x equals 0. So yeah. Now let's think about the function y equals x to the power square root of x. This is a composition of two functions. The outer function is x to the power something. So in that way, it is like a power function, like x square or x to the power third or something like that. It looks like a power function. On the other hand, the inner function is a function of x itself. Imagine it is not square root of x. Let's say it is just x. So we have x in the exponent. In that sense, it is like a exponential function, 2 to the power x or e to the power x or something like that. Now, this time it is like a combination of both power function and an exponential function. We have x in both numerator, in the base and in the exponent. So the best way to deal with this is logarithmic differentiation, because we can bring this exponent to a coefficient or a multiple by taking logarithm of both sides. Taking logarithm simplify many things. So as you can see, by taking the logarithm, we can turn it to ln y equals square root of x times ln x. A very simple function. It is a product of two functions. One is square root of x, the other factor is ln x. Now you can differentiate right hand side very easily using the product rule and power rule and log of derivative of ln x. Differentiate both sides implicitly. The right hand side, left hand side becomes 1 over y dy over dx. 1 over y dy over dx. For the right hand side, we need to use the product rule. Let's take the first factor and differentiate plus keep the second factor and differentiate the first factor using the power rule. Now you can simplify both sides very easily. So now you can simplify the right hand side very easily. If you want square root of x, divide by x is 1 over square root of x. That's fine. You can choose whatever the format you want. The point is you can simplify this uh, term inside the parentheses a little bit more. Then cross multiply both sides by y, and then you'll obtain the derivative as a function of x. Derivative as a function of x. You see, Uh, the derivative is well defined for all positive numbers, but we have a problem at 0. Do you have any questions? Okay, if you don't have questions, we will move to our next topic. So this discussion was about logarithmic differentiation. Implicit differentiation is one technique, logarithmic differentiation is another technique, and we have another technique called parametric differentiation to differentiate parametric functions. So let's talk about parametric differentiation in our next section. Oh, huh? Okay, let's see. So I will start talking about related rates. And in the middle, I will talk about parametric differentiation. Okay, so that's the plan. Um, so let's go all the way back to our definition of derivatives. Definition of the derivative is slope of the tangent line. And the geometric meaning is slope of the tangent line at that point. dy over dx is slope of the tangent line at a given point. It is a measurement about how fast function is changing at that point. How fast is function is changing at that point. So that is why at different points we have different derivatives, different slope of tangent lines. Uh, if you remember, we motivate our discussion or the derivative definition based on the tangent line to uh, uh, distance time graph. The slope of the distance time graph is speed. How fast is distance changing with respect to time? How fast distance is changing with respect to time? On an average interval, imagine a car is moving so in a straight line from one point to another point. Usually uh, in this journey, the car will accelerate, decelerate, uh, it will the driver will brake or accelerate in the middle, so it has this changing speed from time to time. But usually what we do is we take uh, the total distance it traveled and total time it took to travel the whole distance. What we get is an average speed. But uh, from a point to point, it has different speeds. So this instantaneous speed is not captured by the average speed. To compute the instantaneous speed at that particular point, we need the derivative. Derivative is how fast is distance changing with respect to time at that point. You can say same thing about acceleration. From point to point, we have different accelerations. The total velocity change divided by total time is the average acceleration, not the acceleration at a particular point. It is an average. To compute the acceleration at a point or instantaneous acceleration, we need the derivative. So derivative is measuring how fast is a function changing at a point, not this average things. Now, so derivative has these different meanings. We can use it to measure rates of changes. Say you have this function y equal x square, dy over dx measures how fast y is changing with respect to x. The derivative of y equal xy is 2x. So dy over dx equals 2x. When x is very large, y is changing very rapidly with respect to x. That is the idea. For very large positive x values, y is increasing very rapidly with x. But for very large negative numbers, the y is decreasing very rapidly with respect to x. The sign of the derivative tells you whether it is increasing or decreasing. If the derivative is zero, that means we have a flat point, an instantaneous flat point. We call those stationary points. It can be a maximum, or this zero of the derivative can be a maximum point, can be a minimum point, or it can have some other nature as well. Um, so in this section, we'll talk about related rates. Uh, how fast is something changes relative to some other parameter. So let me give you an example. Uh, okay, so here's an example. I took this uh, from a calculus book, um, which I used to teach a calculus course when I was a graduate school. So I think this is some old American TV show, Gonzo and Morgan. These are some characters. We don't need that. Let's talk about this scenario. So Gonzo is at the top of a 10 feet ladder resting against a vertical wall. You can see it from this picture. So this he- here is a vertical wall. This is horizontal floor, and there is a ladder resting against this wall. Length of the ladder is 10 feet, 10 foot long. Then Morgan comes and pull the bottom away from the wall. Okay, so she goes to this very bottom point and pull it. So now what happens is, now ladder is slipping. It is moving down. The gonzo is moving down. He's falling down. Initially, the Morgan, when the Morgan pulls it, she gave it this velocity, half a foot per second, half a feet per second. So now, as it moves, because of the gravity, there will be an acceleration. There will be an acceleration, and also maybe there's a friction between the ladder and moving ladder and the wall and the floor. So we don't know what happens, but we can see there's the velocity is not constant, even though she pulled this away from a velocity of 1/2 feet per second. It will change with time. Hmm? So this length x and y, initially we don't know the values of those. We could compute this if you know the angle, initial angle. Now what happens is, as the ladder moves, x value increases with time and y value decreases with time. So both x and y are now functions of time t. If you compute dx over dt, you're computing how fast x is increasing with time. That is basically the velocity of this bottom point, velocity of the bottom of the ladder. At the same time, dy over dt computes how fast y is decreasing with time t. How fast this vertical height changes with time t. You can think of it as the vertical component of the velocity of this topmost point. That is the velocity of this Gonzo person. So how can we compute this? So we know when the ladder is moving, x is a function of time t, y is a function of time t. However, x and y are also related to each other. The relation between them is they are two sides of a right triangle. Two sides containing the right angle of this triangle. So we know there is a relationship between sides of a right triangle. That's called the Pythagoras theorem. So x square plus y square must be the square of the hypotenuse. So x square plus y square equals 100. All right. So we only have that relation between them. We don't know x as a function of t. We don't know y as a function of t. But we know a relationship between x and y. And also we know both are functions of time t. So take this equation and differentiate it with respect to t, because we are looking for a velocity, how fast is going so falling when the bottom is 6 feet away from the wall, and the velocity of the bottom point is 1/2 feet per second. Take this equation, differentiate both sides with respect to t. So for the derivative of x square, think of it as a composition. The outer function is square, inner function is x. It is a function of time t. So derivative will be 2x dx over dt plus 2y dy over dt equals 0. This is an implicit differentiation. Both x and y are functions of time t, but we don't know the relationship between x and t explicitly. Now, to find how fast Gonzo is falling down, that means how fast y is changing with respect to time t, you can uh, find dy over dt. We should find dy over dt. So dy over dt equals minus x divided by y dx over dt. Um, so we can compute dy over dt if we know x, y, and dx over dt. Dx over dt is given. They say this Morgan pulls the bottom away from the wall at this much. Um, so 1/2 feet per second. So dx over dt is 1/2. And x is 6. X equals 6. And using this Pythagoras relation, we can compute y value when x equals 6. So when x equals 6, y must be 8 beats. Now substitute everything into this equation and compute dy over dt. It is negative 3 divided by 8. It is negative because y value is decreasing with time t. So we have computed the speed of this uh, falling Gonzo, right? So usually a problem like this, uh, the solution to a problem like this can be break into some simple steps. The first of all, when you have a word problem like this, the word problem contains a lot of information. It says the ladder is 10 feet long. Initially, the ladder was this vertical velocity of 5 feet, half a feet per second, and all these things. It can be more complicated than the simplest problems. So, whenever you have a problem like this, convert it to a picture. Draw a picture, mark all the information on the picture. And so in that way, you can comprehend it very easily. Now, um, and make sure you have marked all the informations on the picture. The next step is usually identifying the variables. So, what kind of function we need, what are the independent variables, what are the dependent variables. Here it is somewhat simple because we need how fast is also falling. That means to measure how this speed, the independent variable must be time t. And since he is falling down, it must be how fast this vertical height changes with respect to time t. So t must be a variable, the vertical height must be a variable. And what we are given is how fast is this vertical, so horizontal length change with time t. So we are given dx over dt. Sometimes we are given the row function values, sometimes we are given the value of derivative, or sometimes we may be given the second derivative, we don't know. So we need to understand or identify the variables and some given initial values of the variable. Uh, then differentiate so you need to, after identifying the variable, you can make an equation. So here we made this equation using the Pythagoras theorem. But in addition to that, it may be you need to come up with some equation. Let's say you are talking about uh, let's say you need not how fast length changes. Let's say you're talking about the growth rate of some plant. So when the plant grows, the the area covered by the this plant increases. So in that case, you are talking about how fast an area is changing with respect to time t, something like that. So you need to make an equation, then implicitly differentiate the equation. Implicitly or logarithmically or whatever the technique you have, whatever the appropriate technique for the problem must be used to differentiate the function. So finally, uh, identify what you need to find, substitute the appropriate values and solve it accordingly. The most important part is to convert the given information into some sort of picture and identifying the variables. Do you have any questions? Do you have any questions about this problem? Okay, so I suppose it is clear. So let me move. Uh-huh. Here are some things that you should not do. Don't plug the numerical values in before differentiation. That's really good. It's a really important advice. Now, think about this relation. If you substitute x equals 6, you'll get 6 square equals y square plus 10 square. That computes you the value of y when x equals 6. But you cannot use that equation for differentiation because in that particular instance, you can compute this value of y. Y is no longer a function of time t when you substitute a particular value for x. For that x value, you will have a single y value. So you cannot substitute and differentiate later. Once you substitute, that gives you a numerical value. To differentiate it, take it as a function. Include units in the answer. Check the units work out. That's also a really good answer. So here you have x and y. So in this relation, x and y are of units of length. Here they use feet. It could be meters, inches, centimeters, whatever the measurement that they are using in the problem. So when you differentiate x with respect to time t, so that means you are measuring how fast x is changing with respect to time t. So that changes the unit. It changes the unit of x. So initially it was feet. The derivative will have feet divided by units of feet divided by time t. seconds. So dx over dt is as units of feet over seconds. If you differentiate it one more times, it will be feet over second square. ms minus 2 in SI units. Check the sign of your answer. If the quantity is decreasing, the derivative must be negative. If the relevant quantity is increasing, derivative must be positive. That's also another good advice to check whether we are doing things correctly. Sometimes when we are making the equation, we need some formulas. They may be formulas for areas, formulas for volumes, and other things. So here are some very common geometric shapes and their volumes and surface areas. I suppose you already know these formulas, so don't worry about that. Think about this. Look at this problem. In this problem, somebody is pumping air into a spherical balloon at the rate of 3 cubic inches per second. Okay, so they have connected this balloon to some kind of motor or some kind of pump, and the pump is pumping the air into the balloon in this rate 3 inches per second. So when the balloon is when we are inflating this balloon, the radius increases with time, the surface area is increasing with time. So if you think about what we are given here, they are given how fast volume is changing with respect to time. So this rate may be a constant rate, or it may be not a constant. So imagine what happens even if the balloon, so it can happen that when the balloon becomes larger and larger, these pumps get slower and slower, and this rate may be not a constant, it may be changing with respect to time. Or it may happen that it is a constant, we don't know. For the problem, we have to assume that it is a constant rate. They have not mentioned anything about that, but I think we can say this is a constant rate. Now, let's say how fast is the radius changing when the radius is 2? So when the rate of change of radius, or if the radius is r, dr over dt, is now, it is not a constant. Even if we are inflating the balloon at a constant rate, dr over dt is changing. I will show you. So first of all, it is better to draw a picture of a balloon and mark these informations on the picture. dv over dt equals 3, and at this particular instance radius is 2, and they're asking us to compute how fast is the radius changing. That means dr over dt. We need dr over dt. So it is better to draw a picture in a side and mark all the information and identify variables. There are 3 variables according to the problem. V is one variable, radius is another variable, and t is another variable, time. Both volume and radius are changing with respect to time t. So t is the independent variable, and V and R are the dependent variables. Volume and radius are the dependent variables. Uh, so what can we do? Again, we are not given VOR uh, as functions of time t explicitly. Um, um, but we know a relationship between volume and radius. Since this is a spherical balloon, we can use the formula for the volume of a sphere. V equals 4 divided by 3 times pi r cubed. It's a very well known equation. So that gives us a relationship between V and R. And now as we are inflating the balloon, both V and are changing with time t. So take this relation, implicitly differentiate both sides. So you'll get dv over dt, the right hand side. 4 pi divided by 3 is a constant. Derivative of r cubed with respect to t is 3r square dr over dt. You can simplify both sides and write down dr over dt in terms of dv over dt. You see, dr over dt is 1 over 4 pi r square dv over dt. Even if dv over dt is a constant, dr over dt depends on r. So they are inflating this balloon at this constant rate. As the balloon gets bigger and bigger, uh, the rate of change of radius becomes smaller and smaller, because at the beginning balloon will get bigger very quickly, but as it becomes larger and larger, you won't see the uh, increase of radius uh, quickly. It gets bigger and bigger. As it gets bigger and bigger, radius rate of change of radius becomes smaller and smaller. So when r equals 2, you can compute dr over dt. The rate. So if you think about a bug sitting on the skin of the balloon, this is the speed. Oh, this is how fast this bug moving away from the center of the balloon. All right. At the same time, somebody can come and ask you how fast is the surface area of the balloon changes. Um, for that, so like you have a relationship between volume and radius, we have a relationship between S and radius, right? Surface area and radius. You can take this equation, S equals 4 pi r square, differentiated with respect to t. That will give you the rate of change of surface area with respect to time t, and you will have dr over dt in it. Now that you know dr over dt, at this particular point you can compute ds over dt at that particular point, r equals 2. So you can compute all these things. At different points, you'll have different rates, but uh, still you can compute how fast one quantity changing with respect to another quantity. If you think about volume as a function of R, you could compute dV over dr. dV over dr and dV over dt are two different things. dV over dr computes how fast volume changes with radius. dV over dr, the units of dV over dr will be units of V divided by units of R. That means square meters. But dV over dt has different units. It is m cubed s minus 1. How fast is this volume changes with time. Those are different things. They have different physical meanings. So don't get confused. When you differentiate something with respect to another thing, this independent variable, your choice of independent variable makes a difference. If it is time, you're computing how fast it changes with time t. If your independent variable is radius r, you're computing how fast volume is changing with respect to radius. So there is a very clear difference between those derivatives. Uh, it's quite like it is not give it a like a physical meaning, but it is what it is. If you want, you can take this formula for volume and formula for surface area and remove R from both the equations and get a relationship between V and surface area, volume and surface area. You can do it, right? Uh, you can write an equation that contains just some power of volume equals some constant times another power of surface area. By differentiating this new equation you can compute dV over ds, how fast volume is changing with respect to surface area. So that means for a when the surface area increased by 1 unit, how much the volume increases, or something like that, something along that line. How much this volume changes when the surface area increased by a single unit instantaneously. Um, let's move to another problem. These are very like simple applications of derivatives, but they tells us a lot. If you know the power of this pump, the, if you know how fast is this pump inflating the balloon, you can compute a lot of other things in the process. Um, all right, so think about, look at this problem. It's something interesting. A particle is moving along the parabola y equals x cubed plus 3. When x equals 1, its horizontal velocity is 5 meters per second. What is the vertical velocity at that point? Uh-huh. So imagine this graph or this parabola y equal x cube. So you need to imagine it. I'm not going to draw it. So my writing pad is not compatible with this new computer. So I don't have a way to draw it, but I think you can imagine it. Imagine this parabola y equal x cube plus 3. That's the regular y equal x square parabola lifted up by 3 units. Hmm? Think of it as a metal wire. Hmm? And let's say a bead or a bug moving along the parabola freely under the gravity. So take a bead and lose it from a very high point, and then it moves under the gravity and goes up, like come down and goes up. So this particle is moving along this parabola. At any point, uh, this particle has a velocity. It has a horizontal component and a vertical component. The horizontal component measures how fast x is changing with respect to time t. The vertical component measures how fast the vertical height or y coordinate is changing with respect to time t. So draw a picture of this parabola, and also mark a particle moving on the parabola. When x equals 1, we are given the horizontal velocity. That means we are given dx over dt. When x equals 1, dx over dt equals 5. Uh, this whole thing depends on the initial portion of this uh, particle moving under gravity. So we know when x equals 1, dx over dt is 5. And they ask us to compute the vertical velocity at that point, dy over dt. Both x and y are functions of time t. Both of them changes with time t. We are not given x and y separately as functions of t, but we are given a relationship between them because this particle is moving on this parabola. If it was a different curve, it will have different trajectory, different velocities, a completely different motion. But here it is a parabola. It is moving on a parabola. So take this equation and mark everything on the picture. And we know x and y are related by this equation, and they are functions of time t. Take this equation and differentiate it with respect to t. This is an implicit differentiation. When x equals 1, dx over dt is 5. Substitute it into the equation. Simply compute dy over dt when x equals 1. When x equals 1, the y coordinate is 4. So at the point 1 comma 4, where, vertical component of the velocity is 10. That means y is increasing with time t. That means the particle is moving upward at that point. You see, this is a simple uh, calculus problem. But if you think about this motion, it is a complicated motion. This particle is moving along a parabola. So it is not a motion along a line. Therefore, you cannot use those formulas that you know from physics. In physics, when a particle is moving along a line, you have this set of equations. V equals ut plus at. V equals U plus AT, then S equals UT plus half AT square, V square equals U square plus 2AS. Those equations, those are only valid uh, for a motion along a line. This time the particle is moving along a parabola. So you cannot use those old formulas to compute velocities or accelerations or things like that. Um, you can compute even accelerations. Take this derivative and differentiate it one more time. When you differentiate, you will get d2y over d t2 d2x over d t2 second derivatives. So you can compute uh, accelerations as well. Uh-huh. So I think, yeah, Hafna is asking a very good question. Why is the units of this velocity is m2 over s? That's a really good question. This particle is moving along this parabola y equal x square plus 3, and they say when x equals 1 meters, the horizontal velocity is 5 ms minus 1, so 5 meters per second. When y is measured in meters, the units of, sorry, when x is measured in m, then the unit of x uh, is meters, y units of y must be meter squares or square meters. So rate of change of y with respect to t must be square meters per second. So that's not a linear relationship between x and y. That is why uh, uh, this like unusual units come up in the problem. Y is not really a length; it is something like a uh, area, because y and x are related by the square relationship, right? Right. Let's see. Let's move on to another problem. Car A is driving west towards an intersection at 50 miles per hour. Car B is driving north towards the same intersection at 60 miles per hour. So you can see it from this picture. So this car A is moving towards west at 50 miles per hour, a constant speed, and B is moving towards north at a different speed, and both of them will pass this intersection point. Um, I don't know whether they'll hit each other, or I don't know what will happen. Uh, Now, at some point, uh, A is zero point 0.3 miles away from the intersection, and B is 0.4 miles away from the intersection. The problem asks how fast are they approaching each other when A at this distance. That means how fast the distance between them changes. That's what we say. That is the meaning of how fast are they approaching to each other. That means how fast is the distance between them changes. The distance between them is not x, not y. That's the length of this hypotenuse. So draw this picture, mark A and B, and we are given the rates of changes of x and y. X is decreasing with time. So dx over dt is negative 50 miles per hour. Dy over dt is minus 60 miles per hour. So we must have this sign also, the algebraic sign. Otherwise, the answer will be wrong. We don't know the sign of dz over dt. It may be positive, it may be negative. For example, now imagine B passes the intersection before A. Then, as B approaches to the intersection, as A approaches to the intersection, B is leaving the intersection. In that case, the Z will increase, but still they have this. They are still having the same speeds. So it is very important to have this algebraic sign. So at a particular point, they have these speeds, and x equals 0.3 and y equals 0.4. We have this implicit relationship between three quantities, x, y, z. X and y and z all are functions of t. So take it, differentiate with respect to t. So what we need is dz over dt. So write the equation so that we can compute dz over dt. That means make it into the subject. So x over z dx over dt plus y over z dy over dt equals dz over dt. Compute z value for x equal 0.3 and y equals 0.4. Again, using the Pythagoras theorem. According to the Pythagoras theorem, z must be 0.5 miles. 0.5 miles, and substitute everything into this equation. At this particular instant, z is decreasing. That means they are approaching towards each other. At that point, dz over dt is minus 78. It is decreasing at this rate. Okay, let's see. Devini is asking why it is negative. The speed. The speed is negative because as A approaches to the intersection, as A is heading towards the intersection, X is decreasing with time t. X value is decreasing. Also, Y value is decreasing with time t. So when the dependent variable is decreasing with time t, that means the derivative must be negative. Increasing means derivative is positive, decreasing means derivative is negative. That's a good question. Are there more questions? Any other question? David, did I answer your question? Oh. Right. Let's move on. Now, here is another interesting problem. Example number 5. The radius of a circular cylinder is increasing while its height is decreasing in such a way that its volume remains constant. Okay, so we have this circular cylinder. It is changing its shape in a very strange way. It changes in such a way that its radius increases. When that means it's like more like it is spending this horizontal distance at the same time. Excuse me. Sorry for that. So it increases its radius. At the same time, its height decreases. That means it gets spread horizontally and vertically it's shrinking. So and still the volume is same. That means volume doesn't change. So let's think about this. R is increasing. So dr over dt must be positive. And height is decreasing. That means if you say height is h, dh over dt is negative. If the volume remains constant, that means it does not change with time t. Then dv over dt equals 0. dv over dt is 0. Find the relationship between the rates of change of the radius and the height. That's a very good question. So write down the formula for volume of the sphere. V equals pi r square h. It is the volume of a cylinder. Now, as this cylinder is changing its shape, R increases, I decreases, and volume remains a constant. So think of all of these as functions of time t. Take the equation and differentiate with respect to t. The left hand side is dv over dt. Pi is a constant, r square times h. Both r and h are functions of t. So we must use the product rule. r square dh over dt plus dh over dt, sorry, r square dh over dt times, sorry, plus h times dr square over dt, dr square over dt. That means we need to use the power 2r dr over dt. And since dv over dt, volume is constant, dv over dt equals 0, that gives us a relationship between dh over dt and dr over dt. Both r and h are positive quantities. Dr over dt is a positive quantity, but dh over d is a negative quantity. So this can happen. First term is a negative one, the second term is a positive one. So the sum can be zero. If somebody wants to compute dh over dr, not dh over dt, I mean dh over dr. Look at this purple color text in the right hand side. We have this relation called uh, the parametric, this is, in a way, this is the chain rule. Sometimes we call this the parametric derivative equation for the parametric differentiation. We did not discuss this, but I will discuss it in the next class. If you know dH over dt and dr over dt, when we take their quotient, this dt goes away. That gives us dH over dr. Using this idea and the equation we derived, we can compute dH over dr if you want. So this, for this very strangely behaving cylinder, we have this uh, equation. Sometimes uh, by observing a motion of something or some process which some quantity changing with time, we can come up with an equation like this. Let's say we don't know the formula, volume, or something like that, but we can sometimes come up with a relationship between derivatives. By directly observing this physical system or process, we can come up with a relationship between derivatives. Now, this relation is called a differential equation because you have an equation containing derivatives. There are ways to solve this and make find h as a function of r. So when you have a differential equation, there are ways to solve it. Sometimes it's easy, sometimes it's quite difficult. The solving differential equation is a different skill. It is not like a regular algebraic equation. It is something different. But sometimes most of the time it is doable. You can solve the differential equation and find a solution to the system. Right? Do you have any questions? Do you have any questions about that section? Right. Uh, um, so sometimes we can, not sometimes, we can apply these techniques that we uh, learn in this section, learn under differentiation to all the other fields. It could be physics, in biology, in chemistry. Not only in those fields, we can apply those in economics uh, and see how the market changes or price changes as the supply increases, the demand increases. There are a lot of things we can do with derivatives. Uh, because derivatives are nothing but rates, how fast something is changing. And those that derivative is like not just a rate, it's an instantaneous rate. How fast something is changing at a particular point. It is not an average rate, instantaneous rate. Because rate is also changing from time to time, right? When you have an average rate, that means it's something applies to the whole period. If the period is large, the average won't tell you that average is not like that much relevant. But an instantaneous rate tells you how fast it is changing right now. So in physics, we are doing a lot of these kind of stuff. So derivatives have really good applications in physics, especially how fast is position or displacement of a particle changes with time t gives you velocity. How fast is distance changing with respect to time gives you speed. Remember, displacement and distance are two different things. Displacement is a vector, it has a certain orientation or direction. Distance is something different. So, how fast is displacement changes means velocity, how fast distance changes means speed, how fast velocity changes means acceleration. In fact, Newton came up with the idea of derivatives by thinking about velocities and accelerations. He wanted a method to compute velocities and accelerations at a point. This is really important if you think about planetary motions and things like that. When the planet moves on an elliptical orbit, the distance between sun and the planet um, is changing. It is not a constant. So sometimes, like you can assume approximate the elliptical orbit by a circular orbit and two computations. That will give you an approximate answer, not the exact answer. To get the exact answer, you need to use this elliptic orbit. So to do that, you cannot use this old method of taking average velocities or average accelerations. You need instantaneous velocities and instantaneous accelerations. Hmm? So um, Newton came up with this idea of differentiation because he was a physicist. He was studying these mechanical systems, not only planetary motions, motion of a pendulum, uh, motion of a uh, um, particle or like a solid ball in a let's say, viscous fluid inside the viscous fluid, or motion of a water drop, like a rain drop. So all of these things, and for all of these things, we need instantaneous rates. So that is why those were important at that time. We don't have enough time to go through this section, but let me leave it here. Please go through this section. Please go through this notes. This is here. This section is called "What This Got to Do with Physics." 3.7. That means applications of derivatives in physics. And also I have posted the notes for the other section, 3.8. It is called applications of derivatives in biological sciences. I included these two sections in the discussion because you already know physics and your biology majors. So having a solid understanding of why we need derivatives is very important. These notes are already in the LMS, so please go and look at those. Uh, Also, you submitted the first assignment last Friday, I think. Uh, if you do, you should have the access to LMS by this point, because last time when I checked it, there were 500 some students. That means they have somehow, because of this problem, they have included even the math majors into our LMS. So you cannot just uh, all of you must be in the LMS by now. Or so when you said only 3.1 to 3.5 notes are in LMS. Okay, I'll check it today. Also, I'll post a second assignment. This time, you'll have to compute derivatives using various different rules. Computing derivatives using different techniques. All right. Do you have any more questions? If not, I will close the Zoom session, and as usual, we will meet next Monday. I will post the assignment sometimes this week. Maybe today afternoon or tomorrow. Oh, some of you did not get my email yesterday. Okay. I updated my email list, but I'll check it anyway. All right. Have a nice day.